Hey guys, welcome back to my channel, Math Sprint, and you are watching the ninth video of my calculus crash course. Today, I'm going to be explaining one of my favorite topics in integration, approaches to integration. Now, before we begin, make sure you're familiar with at least these concepts, which will be very important if you want to understand this chapter in calculus. So first understand these concepts and then continue with this video. The topics to know are basic algebra, trigonometric identities, polynomials, set notation, basic coordinate geometry, how to plot a graph on a Cartesian plane, functions, limits and continuity, differentiation as fundamental rules, how to perform differential calculus on different types of functions, the definition of an integral, and the basic rules of integration. If you want to understand the basic rules of integration and differentiation, you can check out my earlier videos on calculus, which covers these topics. Do note for this video, I'm only working with real numbers and not imaginary numbers. Okay, so first I'd like to introduce a little bit about differential equations. So a differential equation is an equation that involves derivatives of an unknown function. If we want to solve differential equations, we need to find the function that satisfies it. When the derivative function f dash of x is given, we integrate to find all the possible functions such that the integral of the f dash of x with respect to x gives f of x plus c. It's called a general solution to a differential equation. Sometimes we may know certain values of f or f dash called initial conditions. They help us to find the particular solutions, which are the specific functions of f of x, possible functions. So let's do an example. So we need to find the equation of the curve that passes through 2 comma minus 1, this point, and whose slope is at any point x comma y is 4x cubed. So we need to analyze this question right now. So recall your knowledge of tangents and derivatives. In this problem, the slope at any point is given by the equation 4x cubed. So what this pretty much means is dy by dx is equal to 4x cubed. Here's the thing, dy by dx, even though is not a fraction, technically speaking, it does behave like one at certain times. Think of dy as an infinitesimal small change in y, and think of dx as an infinitesimally small change in x. So we can rearrange the terms so that dy is equal to 4x cubed dx. So what this means is that any small change in y, extremely small, negligible change in y, is equivalent to 4 times the x cubed times the infinitesimally small corresponding change in x. So what we do is we integrate both sides into the equation. The equation of the curve becomes y is equal to x to the power 4 plus c. Remember, c is the constant of integration. Now you might ask, since we're integrating both sides, why we don't put a constant of integration on the left and right sides of the equation. The reason is that actually doesn't matter, because c is just an arbitrary constant that will encompass any of those smaller constants that we create. So now we got to find out what exactly c is, like what's its specific value. Now in the problem mentioned that the curve passes through 2 comma minus 1. Good, we can use this. We substitute x with 2 and we substitute y with minus 1 in the equation. We end up discovering that c is minus 17. Therefore, the equation of the curve that passes through the point 2 comma minus 1 and whose slope function is 4x cubed is y is equal to x to the power 4 minus 17. Okay, so now let's suppose we have a problem where we need to solve dy by dx is equal to xy. Basically, what we need to do to solve it is to find y in terms of x. We start off with dy by dx is equal to xy. We take y to the left and dx to the right. So now we get dy by y is equal to x dx. So we integrate both sides, and remember, integrating 1 by y with respect to y, we'll just get ln y. And I'm not going to put a constant of integration here. I'll just add it to the right-hand side only after the integration is all done. It's just an arbitrary constant after all. So we integrate x with respect to x to get x squared by 2 plus c. So now I added the constant of integration, that is c. So use algebraic manipulation right now. So we get y is equal to e to the power of x squared by 2 plus c. Now here's something important. In the context of this problem, it may seem to have It may seem like in this scenario, what I'm about to say has less relevance because there's less information, but I'm trying to expand your perspective here. Now, suppose we have a problem with real values. Rather than use the information to find C specifically, let's use it to find K. Now, what is K? We're letting K be the constant e to the power of C. Now, why am I asking you to find K? Well, if we try to find C, it is likely that our values could get a bit less accurate working with a lot of decimal values. But if we just find K, it's a lot easier to work with. Okay, so I want to introduce some important trigonometric integrals. Here, A is a constant, not a variable. Keep that in mind. So integrating 1 by the square root of a squared minus x squared with respect to x produces arc sine x by a plus c. Integrating 1 by x squared plus a squared with respect to x creates 1 by a arc tan x by a plus c. Integrating 1 by x square root of x squared minus a squared with respect to x produces 1 by a arc sec x by a plus c. Okay, so now that we got that done, now let's move to the first approach of integration, the method of substitution, also called U-substitution. So how does it work? So we substitute a portion of the function being integrated with some temporary variable. Now, conventionally, this variable is represented as u or t, but you can choose your own variable. We perform differentiation on the temporary variable and use algebraic manipulation to express the integrand in terms of the temporary variable. The portion of the original function that is equal to the temporary variable is resubstituted back after the integration is done. Now, the reason we do this is to express the integrand into a form that can be more easily integrated. So just so you know, this approach partly involves a bit of intuition and problem-solving experience. So to get better at it, you need to do more problems. Okay, so let's do a sample problem here below. We need to integrate the square root of 3x plus 4 with respect to x. So we get a temporary variable u. We let u be equal to 3x plus 4. We've chosen this because I have a feeling, okay, this is going to work right now. So then we differentiate u with respect to x. Du by dx is equal to 3. We rearrange the terms and we find that dx is equal to du by 3. Now substitute these values into the integral. So now our original integral of 3x, square root of 3x plus 4 with respect to x becomes the square root of, the integral of the square root of u by 3 with respect to u. Now think about the way we've changed this integral. It's a lot easier to integrate this one. So you just use the basic rules of integration right now. We end up with 2 by 9 u to the power of 3 by 2 plus c. Now substitute u back with 3x plus 4. We get 2 by 9 times 3x plus 4 to the power of 3 by 2 plus c. If you want, you can differentiate just to check if this method really works, but it will. Let's do some sample problems. The first one. We need to integrate x times the cube root of 3 minus 8x squared with respect to x. So we're going to let our temporary variable be u is equal to 3 minus 8x squared. Let's differentiate this. So du by dx is equal to minus 16x. We rearrange the terms to get us x dx is equal to minus du by 16. So now let's substitute all this into the original integral. So since we know that x dx can be changed into minus du by 16, we also can figure out that the cube root of 3 minus 8x squared can be changed into the cube root of u. So now the integral has changed into minus 1 by 16 times u to the power of 1 by 3, and we have to integrate this with respect to u. Now we can use the basic rules of integration. Minus 1 by 16 is a constant that can be put outside the integral. The cube root of u can be integrated with respect to u, so that becomes u to the power of 4 by 3. The whole thing is divided by 4 by 3, so that just basically 3 by 4 u to the power of 4 by 3. So we multiply 3 by 4 times u to the power of 4 by 3 with minus 1 by 16. This gets us minus 3 by 64, u to the power of 4 by 3 plus c. Now we can substitute u back with 3 minus 8x squared. So it becomes minus 3 by 64 times 3 minus 8x squared to the power of 4 by 3 plus c. Okay, here's another problem below. We need to integrate e to the power of x times tan e to the power of x with respect to x. So we're going to set our temporary variable u to be e to the power of x. Now differentiate u with respect to x. Du by dx is equal to e to the power of x. Rearrange the terms so that du is equal to e to the power of x dx. Now let's put this into the integral. Tan e to the power of x is changed into tan u. So e to the power of x tan e to the power of x dx can be changed into tan u du. So now we integrate this. Recall the rule where you integrate tan x with respect to x and you get ln sec x plus c. So we integrate tan u with respect to u and you get ln sec u plus c. And we can substitute u with e to the power of x, so we finally get ln absolute value of sec e to the power of x plus c. Now, how did I decide in both of these problems to make u as 3 minus 8x squared or u as e to the power of x? Where here it gets a bit more intuitive. I'm having problem solving experience, I can be able to use these sort of internal methods in my mind to figure out which is the best form of substitution that will most easily work for me. All right, another one. So we got to integrate cos root x divided by root x with respect to x. We have our temporary variable u, which we equate to root x. Again, we differentiate u with respect to x. So du by dx is equal to half x to the power of minus 1 by 2. We rearrange the du is equal to dx by root x. Okay, so now let's take a look at our integral here. Dx by root x is equal to 2 du. So we substitute dx by root x with 2 du. Also, root x can be substituted with u. So our integral is now changed. Now we have to integrate 2 cos u with respect to u, and this gives us 2 sine u plus c. So now we get rid of the temporary variable u by substituting it with root x. So our final answer becomes 2 sine root x plus c. Okay, so here's our problem. We need to integrate x plus 1 divided by x squared plus 1 with respect to x. So how do we do this? Now you need to split the functions into 2 smaller functions. So we have x by x squared plus 1 and 1 by x squared plus 1. Now let's get our temporary variable going. Let u be equal to x squared plus 1. So du by dx is equal to 2x. Rearrange the terms and you get x dx is equal to du by 2. Okay, so let's put all this in the integral of x by x squared plus 1. That smaller integral changes to the integral of 1 by 2u with respect to u. Okay, so now these smaller integrals are a lot easier to evaluate. Integrating 1 by 2u with respect to u is just half ln absolute value of u. Integrating 1 by x squared plus 1 with respect to x is arc tan x. So add them together and substitute u with x squared plus 1. So our final answer becomes half ln absolute value of x squared plus 1 plus arc tan x plus c. All right, let's move on to integration by parts. So this is an approach that's mostly used when the function being integrated, also called the integrand, is a product of 2 other functions that we know how to integrate or differentiate. So if we have to integrate f of x times g of x, then we just use this formula which has already been proven. Now, just if you want a confirmation, yes, the formula below here at the bottom of this slide does include an integral inside an integral. So what you need to do is you need to first evaluate the integral inside and then evaluate the larger integral outside. Keep in mind something as well. This is f dash of x, not f of x in the formula over here, which I'm indicating. A common mistake is to assume that this is f of x when you don't remember the formula correctly. So just to confirm, when you integrate f of x times g of x with respect to x, it'll be equal to f of x times the integral of g of x with respect to x minus the integral of, with respect to x, the integral of g of x with respect to x multiplied by f dash of x. Keep that in mind. So the formula shown at the bottom here is actually easier to understand and work with compared to the one directly above it. I would recommend that you pause the video now and take some time to note this formula down and thoroughly remember it. I'll be showing you some sample problems very soon that will help you reinforce this formula in your mind. Generally, practicing is the best way to remember it, but if you're new to this method of integration, it's better to keep the formula written near you. Okay, so now that you know the formula, this is something also important to know. So you may be wondering how you should decide whether to treat a function as f of x or g of x when doing integration by parts. Well, for this method, technically you can use any function as f of x and any function as g of x. It won't affect the final result, technically speaking. But here's the problem. Some functions are a lot more difficult to integrate than others. So we have to choose our functions a bit wisely so that the integration steps are shorter and easier. Now that's where the ILATE rule or ILATE rule comes in. ILATE is basically an acronym that gives the order of preference for which a function we choose should be f of x, and which function should be g of x. The I stands for inverse trigonometric functions. The L stands for logarithmic functions. The A stands for algebraic functions. The T stands for trigonometric functions. And the E stands for exponential functions. The order I, L, A, T, E, and E is very important. See, suppose we have two functions of a different type that we need to integrate. For example, we have an inverse trigonometric function and an algebraic function. They're both multiplied together and we have to integrate them. Now, how do we decide which function to take as f of x and which function to take as g of x? Because that's how this whole formula will work, depending on which is f and which is g. Well, as per the rule, the ILATE rule, the higher preferred function becomes f of x and the other function becomes g of x. So when I mean by a higher preferred function, I mean that the function type is higher in the ILATE order. So since in the scenario I gave you with the inverse trigonometric function multiplied by the algebraic function, the inverse trigonometric function is these types of functions are higher order of preference than algebraic functions. So we take f of x to be the inverse trigonometric function and g of x to be the algebraic function. But suppose we have to integrate, say, two functions of, say, an algebraic function and a trigonometric function. Algebraic functions are higher in ILATE order than trigonometric functions. That is, a comes before t in that order. So we take f of x to be the algebraic function and g of x to be the trigonometric function. But let's suppose we have to integrate two functions of the same type, like two inverse trigonometric functions multiplied together. Then we pick the function that is easier to integrate generally as g of x. Now, if you have trouble memorizing ILATE, that's fine. There's another way of looking at integration by parts that can work at times. A general rule of integration by parts is always put the function that's more difficult to integrate as f of x and the function that's easier to integrate as g of x. So here's one sample problem. We need to integrate x times e to the power of 3x with respect to x. Remember ILATE. Algebraic functions are more preferred than exponential functions as per ILATE. So we let f of x be equal to x and g of x be equal to e to the power of 3x. We know the formula for integration by parts. I put it again here for your reference. Now just follow through with it. Do recall the basic formulas for integration. You could just figure out that the integral of e to the power of 3x with respect to x is 1/3 of e to the power of 3x. You don't need to add the constant of integration for the integral inside the integral here. Now take a look. Remember, you need to evaluate the integral inside the integral first. So look at where I'm indicating with my mouse right now. Over here. Evaluate this integral and then multiply that integral with the derivative of x with respect to x, which is just 1. Then the final answer we get is 1/3 x to the e to the power of 3x minus 1/9 e to the power of 3x plus c. All right, so another problem. We need to integrate ln x with respect to x. So how do we do this? This does not have the product of two functions, but let's look at this differently. Think of ln x as ln x times 1. ln x is a logarithmic function, but 1 is actually an algebraic function. So now we apply ILATE. As per ILATE, logarithmic functions have a higher preference than algebraic functions. So f of x is equal to ln x and g of x is equal to 1. That's how we're going to let be. Now use the formula. Remember that differentiating f of x, which is equal to ln x, will get us 1 by x in this problem specifically. So eventually, we'll end up with the final answer of x ln x minus x plus c. Okay, so now here's a challenging problem. We need to integrate e to the power of x times cos x with respect to x. As per Eilate, trigonometric functions have a higher preference than exponential functions. So we're going to let f of x be equal to cos x and g of x be equal to e to the power of x. Now use the formula. Integrating e to the power of x with respect to x is just e to the power of x. Also, differentiating cos x gets us minus sine x. But you may be wondering now, how do we integrate e to the power of x times sine x, which we got over here? Well, here's the interesting part. We use integration by parts again, just for e to the power of x times sine x. So let's do integration by parts for e to the power of x times sine x. As per Eilate, trigonometric functions have a higher preference than exponential functions. So remember, differentiating sine x with respect to x will give us cos x. And also remember, we only need to add the constant of integration when we are finished integrating completely at the end of the problem. So for now, we don't need to put constants of integration for the integral inside the larger integral or anywhere else. Only at the end of the integration, we could add it. So now we find out an expression for the integral of e to the power of x times sine x with respect to x. Now substitute this expression into the expression we obtained for the integral of e to the power of cos x with respect to x. Now here's something interesting. The integral that we are trying to evaluate, that is the integral of e to the power of x times cos x, is on the left-hand side of the equation, and also the right-hand side of the equation. So if we put those integrals both on the left-hand side and then add them together, we end up with the expression below, which I'm indicating here. We divide both of the sides of the equation by 2, and we end up with the final answer of 1 by 2 e to the power of x cos x plus sine x plus c. Okay, so now we've got tabular integration. So tabular integration is just a good way of organizing the steps of the solution done by integration by parts. I've shown the formula for your reference, but to be honest, it's not that relevant to this, even though tabular integration is just an easier way of doing integration by parts. Okay, so how does tabular integration work? So you have the functions f of x and g of x as always. We're going to choose f of x so that we take derivatives of f of x until we reach 0. And the other function has to be g of x. So what we do is we create a table. You start off with f of x on the left column and g of x on the right column. So on the left column, you keep differentiating f of x and recording these different functions until you reach 0. On the right column, you need to integrate g of x repeatedly over and over again until you reach the column where f of x is 0. So you keep recording all these different values. You keep repeating this until f of x's column has a value of 0. That is, it has a row of 0. Then you multiply the terms, applying the sign in alternating patterns of plus, minus, and so on. Then add all those products. I'll show you how this is exactly done with sample problems. Okay, so let's do a practice problem with tabular integration. We need to integrate x squared e to the power of x with respect to x. So let's arrange this all in a table. So our f of x is going to be x squared, and our g of x is going to be e to the power of x. Now, why did I pick this? Because it's possible to keep differentiating x squared over and over again until we reach 0. But if I keep differentiating e to the power of x repeatedly, it's never going to get 0. I'm never going to get 0. Remember, f of x always goes on the left, and g of x will always go on the right in this format. This organization is crucial for this method, tabular integration, to work. In the first row below the header, just put the functions x squared and e to the power of x in the same row. Now on the left, you differentiate until you keep getting 0. So the derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of 2 is 0. We stop at 0 always for tabular integration. Now remember, always for tabular integration, organization is crucial. You have to always be very organized when doing this. Otherwise, you're going to have a hard time working with tabular integration. Now on the right, we integrate. But the thing is, integrating e to the power of x with x just gives e to the power of x. So you don't have to worry about the constant of integration for now. Just keep integrating over and over again, and you'll get the same value, e to the power of x, over and over again. Now, the multiplication part. So we multiply from left to the lower right. That's how it works. Follow the understand follow the arrows to understand which terms are being multiplied, and pay attention to the sign on each arrow. That's very important. So we multiply x squared with e to the power of x, as shown in the first topmost arrow. Then we multiply 2x with minus e to the power of x. Now, why did I just say minus e to the power of x instead of just e to the power of x? Well, it is because the rule of that rule where you do plus minus alternating. So basically, the topmost arrow has to have a sign of plus. Then the second arrow has to be minus. Then following that is plus. Then following that, if you have more arrows in tabular integration, you have to have plus minus plus minus. That's always how it is, and you have to start with the topmost arrow having a sign of plus. So that you keep alternating basically. So you multiply 2 with e to the power of x. That's the third arrow. Now you have all these terms: x squared e to the power of x, minus 2x e to the power of x, and 2 to the power of x. You add them all together and you end up with x squared e to the power of x minus 2x e to the power of x plus 2e to the power of x plus c. All right, so here's another one. We need to integrate x cubed plus sine x. Sorry about that. We need to integrate x cubed times sine x. So now, why did we choose x cubed to be our f of x and sine x to be our g of x? Why? Because differentiating x cubed repeatedly will eventually lead us to 0. But differentiating sine x, on the other hand, repeatedly will never get you to 0. In fact, if you just practiced enough problem on differentiation, you should be able to realize this immediately. So if I keep differentiating sine x, let's see what will probably happen. I differentiate sine x with respect to x, I get cos x. You differentiate cos x with respect to x, you got minus sine x. You differentiate minus sine x with respect to x, you get minus cos x. And when you differentiate minus cos x with respect to x, you get sine x again. It's like one big circle. So the same thing as in the previous practice problem. You put f of x on the left column and you put g of x on the right column. You differentiate the left column with respect to x, and you differentiate x cubed. So differentiating x cubed will give you 3x squared. Differentiating 3x squared will give you 6x. Differentiating 6x will give you 6. And differentiating 6 gives 0. Now we got to integrate the right column with respect to x. So integrating sine x gives cos x. Sorry, integrating sine x gets minus cos x. Integrating minus cos x gives minus sine x. Integrating minus sine x gives cos x. Integrating cos x gives sine x. Now we do the multiplication. So again, follow the arrows and pay attention to the sign on each arrow. We multiply x cubed with minus cos x. We're not going to multiply 3x squared with minus sine x because of the sign on the arrow. Remember, pay attention to the signs. The minus sign on the arrow and the minus sign on sine x, the minus sign on the sine x would produce a plus. So we multiply 3x squared with sine x. Then we multiply within the third arrow, we multiply 6x with cos x. We multiply 6 with minus sine x because of the minus sign on the fourth arrow. So now we got the terms minus x cubed cos x, 3x squared sine x, 6x cos x, and minus 6 sine x. You add all of these terms together and you get an answer of minus x cubed cos x plus 3x squared sine x plus 6x cos x minus 6 sine x plus c. We only need to add the constant of integration when we are finished integrating completely at the end of the problem. Okay, so I'm going to give some guidelines on how to approach integration with large powers of trigonometric functions. Suppose we have to integrate sine x to the power of a positive odd integer n. In an actual problem, you probably will get a specific value of n, but this is just for general cases of odd values of n. Then what we do is we factor sine to x to the power of n and change it into sine x to the power of n minus 1 times sine x. So we know that since n is odd, n minus 1 will be even. We express sine x to the power of n minus 1 as sine square x to the power of n minus 1 by 2. We can then use the identity sine square x is equal to 1 minus cos square x. Then we use the method of substitution to evaluate the integral, and our temporary variable u will be u is equal to cos x, and then you use u substitution accordingly. And now suppose we have to integrate cos x to the power of the positive odd integer n. In an actual problem, again, you'll probably get a specific value of n, but this is just for general cases. So what we do is we factor cos x to the power of n so that it changes into cos x to the power of n minus 1 times cos x, a different way of expressing it. So we know that since n is odd, n minus 1 is even. Again, we express cos x to the power of n minus 1 as cos square x to the power of n minus 1 by 2. We can then use the identity cos square x is equal to 1 minus sine square x. We substitute this into the cos square x to the power of n minus 1 by 2. Then we use the method of substitution again to evaluate the integral, and our temporary variable u is going to be have the value u is equal to sine x. Then we use u substitution accordingly. Now suppose we have a similar problem of integrating cos x to the power of n or sine x to the power of n with respect to x, but here n is an even positive integer. So what we do is we use the half angle formula. You should recall your knowledge of trigonometric identities, and you should know that sine square x can be expressed as 1 minus cos 2x by 2. You should also know that cos square x can be expressed as 1 plus cos 2x by 2. You can use these identities in the integrand. Then you expand the integrand using algebra. After that, you use whatever methods are necessary, like u substitution or integration by parts and so on. Just so you know, in some problems, they may attempt to intimidate you by giving you large powers or large coefficients of x inside the trigonometric function. The way to solve these problems is to look at the half angle formulas in a different way. Cos squared 2x can become 1 plus cos 4x by 2, or even sine squared 6x can become 1 minus cos 12x by 2. You should be able to broaden your perspective to think like this, and then you can tackle such problems. Okay, now suppose p is an odd integer and q is an integer, but it doesn't matter whether it's odd or even. We need to integrate sine x to the power of p times cos x to the power of q with respect to x. Generally, p and q will likely be positive integers. So what you do is you factor sine x to the power of p, so it becomes sine x to the power of p minus 1 times sine x. Now you use the identity sine square x is equal to 1 minus cos square x again, in sine x to the power of p minus 1. Because we know p minus 1 is even if p is odd. Then we use the method of substitution, also called u substitution. Here our temporary variable u will be equal to cos x. So that way du is equal to minus sine x dx, and you perform u substitution accordingly. Okay, another one, similar situation. We need to integrate sine x to the power of p times cos x to the power of q with respect to x. But here, q is an odd integer. P is an integer, but it doesn't matter. It does not matter whether it's even or odd. So we express cos x to the power of q as cos x to the power of q minus 1 times cos x. We use the identity cos square x is equal to 1 minus sine square x in cos x to the power of q minus 1, since we know q minus 1 is even as q is odd. Then we use the method of substitution, also called u substitution, and here our temporary variable u will be equal to sine x, and du will be equal to cos x dx, and we perform u substitution. But now here's a special case. Suppose p and q are both even. We use the power reducing formula. Sine square x is equal to 1 minus cos 2x divided by 2. Cos square x is equal to 1 plus cos 2x by 2. And after that, we just expand. Expand accordingly and integrate afterward using the appropriate methods. It can be u substitution or integration by parts. Now, suppose p is an odd integer. Q is an integer, but whether it's even or odd does not matter. We need to integrate tan x to the power of p times sec x to the power of q with respect to x. So what we do is we factor both tan x to the power of p and sec x to the power of q. The integrand becomes tan x to the power of p minus 1 times sec x to the power of q minus 1 times tan x times sec x. Since p is odd, p minus 1 is even. So we employ the identity tan square x is equal to sec square x minus 1 in tan x to the power of p minus 1. Now we use U substitution. We let u be equal to sec x, differentiate u with respect to x, rearrange the terms, and we get du is equal to sec x tan x dx. Now suppose q is an even integer. P is an integer, but whether it's even or odd doesn't really matter. We need to integrate tan x to the power of p times sec x to the power of q with respect to x again. So what we do is we factor sec x to the power of q only, changing it to sec x to the power of p minus 2 times sec square x. Since q is even, q minus 2 is also even. So we use the identity sec square x is equal to tan square x plus 1 in sec x to the power of q minus 2. Then we use the method of substitution. We let u is equal to be equal to tan x and differentiate and rearrange the terms so that du is equal to sec square x dx. Then we substitute this into the integral and perform integration. Now suppose if p is an even integer and q is an odd integer, and you need to evaluate the integral of tan x to the power of p times sec x to the power of q with respect to x. So there's no standard method of evaluating these type of integrals, to be honest. Integration by parts could work, or maybe some other way. Usually intuition and problem-solving experience will come in handy here when approaching such problems. Okay, so you may encounter integrals with quadratics. It's useful to use methods like completing the square to make your work easier when evaluating integrals. I've put the method for completing the square here for quadratic equations of the form ax squared plus bx plus c. This is a concept you should understand already. I would recommend that you revise this concept a little if you can't recall it. Okay, so let's do a practice problem. We need to integrate 1 by the square root of 2x minus x squared with respect to x. So let's complete the square method. Usually complete the square method for 2x minus x squared. We can express 2x minus x squared as 1 minus x minus 1 the whole square. Now let's use U substitution. We let u be equal to x minus 1. Differentiating u with respect to x and rearranging the terms will show that du is equal to dx. So that pretty much means is infinitesimally small changes in u are approximately equal to infinitesimally small changes in x. So when we can change the integral this way. Now we have to integrate 1 by the square root of 1 minus u squared with respect to u. So we end up with arc sine u plus c. We substitute u with x minus 1, and our final answer becomes arc sine x minus 1 plus c. Okay, so integration of rational functions. So you should know a little about rational functions. They're essentially functions of the form f of x by g of x, where f and g are both polynomials which can be divided by each other. It's possible to decompose a rational function into a series of smaller rational functions. This method is usually called integration by partial fractions. If the degree of f of x is lower than the degree of g of x, and if g of x is the product of different linear factors, then what we can do is that we can express f of x by x minus a times x minus b times x minus c, where x minus a, x minus b, and x minus c are the linear factors of g of x. So you can express this whole thing as a by x minus a plus b by x minus b plus c by x minus c, where capital A, capital B, capital C, and lowercase a, b, and lowercase c are all real numbers, different real numbers, but still real numbers. Okay, so here's some of the basic rules for rational functions. They're relatively straightforward. Basically, the table shows you how to transform a rational function into a series of partial fractions that can be easily integrated. Again, capital A, B, and C, and lowercase a, b, and c are all real numbers. P, Q, and R are all real coefficients, and x squared plus bx plus c cannot be factorized any further. So you may want to pause the video and note all these rules down. They're going to be pretty important. Okay, so let's do a practice problem. So we have to integrate 2x squared minus 9 with respect to x. So how do we do this? The reason partial fractions is needed in this problem is because U-substitution, integration by parts will become really difficult, or any other method will be really difficult. If we want to integrate this smoothly, we should try to decompose this large fraction into a series of smaller fractions, which is more easier to integrate. So recall your knowledge of polynomials here. Let's factor x cubed plus 2x squared minus 3x, that is the denominator, and change it into a product of multiple linear factors. So you should figure out that it changes to x times x plus 3 times x minus 1. You can use the method of induction to figure this out. Now, recall rule number 3 for rational functions, which I showed you in the previous slide. What you should realize is that when we express 2x squared minus 9 divided by x cubed plus 2x squared minus 3x as a by x plus b by x plus 3 plus c by x minus 1, you should figure out that we can express it in such a form. And here again, A, capital B, and capital C are all real numbers. Using algebra, you'll figure out that a times x plus 3 times x minus 1 plus bx times x minus 1 plus cx times x plus 3 is equal to 2x squared minus 9. Sorry. So now how do we figure out what a, b, and c are all supposed to be? Well, here's the convenient part. A, b, and c always met this method. They're always real constants independent of the variable x. It doesn't matter what x is, and that will not affect the value of a, b, and c. So we can input different values of x to help us determine the accurate values of a, b, and c. Sometimes you may need to solve simultaneous equations to arrive at x, just so you know. So what you do is you just plug in different values of x. So I choose to take a scenario where x is equal to 0. I substitute this value into the equation here. What happens is that plugging in x is equal to 0 allows me to eliminate most of the terms. That's convenient. And I can figure out that a is equal to 3. Then I choose to set x is equal to minus 3. I substitute this into the equation that we created over here. I substitute x is equal to minus 3, and what happens is that it allows me to eliminate most of the terms, and I can figure out that capital B is equal to 3 by 4. Then I choose to set x is equal to 1. I substitute this value into this equation here, and what happens is plugging it allows me to eliminate most of the terms, and I can figure out that c is equal to minus 7 by 4. You can try this yourself, actually. And if you don't want to use the values I picked, minus 3, 0, or 1, that's fine. You can pick your own values, but you will likely have to solve 3 simultaneous equations in the process in order to find the same values of a, b, and c as the solutions. Okay, so we have a, b, and c. Well, we plug them in now into our integral. We discover that 2x squared minus 9 by x squared plus 2x squared minus 3x has an equivalent form of 3 by x plus 3 by 4x plus 3 minus 7 by 4 times x minus 1. So now these functions can be integrated separately. You should know the basic rules of integration to be able to do this. We'll eventually find that integrating this large fraction, 2x squared minus 9 by x cubed plus 2x squared minus 3x, with respect to x, will get us 3 ln absolute value of x plus 3 by 4 ln absolute value of x plus 3 minus 7 by 4 ln absolute value of x minus 1 plus c. Again, we added the constant of integration at the end of the integration. Thank you guys, that'll be the end of this video. Make sure you hit those like and subscribe buttons to see my future videos on mathematics. Until then, stay tuned.